Hi, I'm Eric Sabo, and today we're going to talk about anti-gravity. Anti-gravity, the holy grail of physics. At the 2011 World NPA Conference in College Park, Maryland, I had a chance meeting with Dr. William Lucas on the sidewalk. We talked about anti-gravity, and he said, "We need shielding." And I remember saying, "How are you ever going to do that? I mean, the metal shielding boxes don't work, nothing works. The Earth's gravity is a powerful thing. Take a lot of power, whatever it is." I left the conference after a few days because it was, as Walter Babin describes it, unrestricted speculation. Anyway, from the conference, I decided to head over the 50 Bridge at Annapolis up to Dover Downs. While at Dover Downs, I came up with an idea for Bill Lucas's shield. The only possible way to create a shield is to interrupt the gravitational connection between atoms. But maybe we don't need to interrupt, but rather sweep aside the gravitational ether. And I have a great idea for doing that, and here it is. I started constructing the device, and it took 3 years to get to the point I'm at today due to my physical limitations. I really can't travel, so it's too big of a project for me. Here it is, the AGU-1 Mark III. The AGU-1 Mark III. The Mark III is configured here to run 200 amps at 12 volts DC. The rotor is a section of 750 MCM copper cable with 61 strands separated out and equally spaced. There's a start button, emergency stop button, run indicator light, and 3-speed motor switch. The load bank consists of 40 2-ohm 100-watt resistors with 2 each connected in parallel to make 1 ohm. Each resistor pair is switched individually so that the current can be applied gradually. There are 20 switches. There are 4 contactors that are rated for 30 amps at 300 volts DC or 20 amps at 600 volts DC. These are for emergency stop. The 4 contactors pull in together when the start button is pushed, supplying the 20 switches with power. All 4 contactors drop out when the emergency stop button is pushed, safely cutting all power to the unit. This is the digital reader for the load cell that weighs the test weight. The test weight is a piece of PVC pipe, and there is no ferromagnetic material in the test weight. This is the load cell. It is sensitive to 5/10,000ths of a pound. This is the 200 amp DC digital ammeter. And this is its associated shunt. It puts out 75 millivolts at 200 amps and 0 millivolts at 0 amps. This is the laser temperature reader for the brush assembly. Here it is reading the brush assembly temperature. The brushes are diesel-electric locomotive drive motor brushes, and I drum sanded them to contact the rotor from their sides as opposed to the end as they are designed. This is the top set of double bearings with the brush assembly between the bearings. The 166.6 amps is a reading of current flow through the rotor, and the picture is one frame of a static test. The change from single bearings to double bearings was necessary because the lateral tension from the brush assemblies created problems. The rotor, being a piece of 750 MCM copper cable with its strands separated out, has inherent flexibility. The bearings are not precision bearings, so there was considerable wobble allowed, which led to deformation of the rotor. The deformation of the rotor led to the stalling of the drive motor after a short period of runtime. This is the top brush assembly. This is the bottom. There are only 3 brushes in this assembly because the rotor at the bottom is 1-inch L-type copper tubing. When the change was made to double bearings, I shaved a bit off all the brushes and added a 4th brush. The brushes are rated at 120 amps each. 4 would be at least 480 amps continuous duty. I think they could handle at least 900 amps for a short period of time. My power supply is this: 5 12-volt batteries connected in parallel. This setup delivers a clean, steady 200 amps at 12 volts DC. Here's an operational test of the unit. This is a test with rotation, cooling fan on, motor on. Each switch adds 12 amps. And we see brush temperature at 73, 74, 5, 76, 82, 129 amps, 144 amps. 180 amps, 102 degrees, and there's no change in the test weight. It's fluctuating between 0.1365 and 70. That's due to the air flow. We're cutting back. We have a temperature of 128 degrees on the brushes, no change in the test weight. Okay, this is a test without rotation, and we're going to see the brush temperature doesn't rise as much, and I think the temperature rise is due to friction, really. There's no change in the test weight in any of these tests. It's only 12 volts, 180 amps. I could connect my batteries in series and get 60 volts. It would also deliver 200 amps at 60 volts for a short time. But I would then have to buy an additional 120 resistors on top of the 40 I have now for a one-time use. What I really need is this. It's a battery bank for one of the 4 500 kW uninterruptible power supplies. This rack is actually 1/4 of a bank that occupies a whole room. The bank will deliver 1200 amps at 535 volts DC. Now that's serious power. The issue now becomes you need a load bank that can dissipate 300 to 500 kW. This is one battery cell. It weighs around 300 pounds. This is a different room of batteries for a different 500 kW uninterruptible power supply. The idea is to get enough current flow either down or up through the rotor to interrupt the gravitational ether. The test weight hangs inside the rotor from a load cell that will measure any decrease in weight. I think DC current is necessary, but maybe an AC component superimposed is also needed. That's why we do the testing. So the idea is to get enough DC current flowing down through the rotor conductors to achieve the point that the field of each conductor overlaps its adjacent conductors. The result should be a blocking or interrupting or sweeping aside the gravitational ether. Then we'd see a decrease in weight in the test weight because it's isolated from the ether. So why DC current? Because the field around the conductor remains constant with DC. That's why you can't use a clamp-on ammeter for DC current. You need a shunt that's in line with the DC current flow to get a reading. I have this 200 amp shunt. I also have a 1000 amp shunt. They both put out 75 millivolts at their rating. The problem is my readout reads 200 amps at 75 millivolts. So with this 1000 amp shunt, at 1000 amps it will read 200. You just have to multiply your reading by 5 for actual current flow. Bottom line is 200 amps, 12 volts DC is only 2400 watts, a couple of hair dryers. It's going to take way more than that. There are 61 strands in the rotor, and if you want a current flow of 10 amps through each strand, well, that's 610 amps. And I would kind of like to see 20 amps, so that's 1220. That's a lot of juice. The idea is this: when the current flows through a conductor, an electromagnetic field forms around the conductor. The overlap would block or sweep aside the ether. Now, Einstein shows us that as you accelerate to c, the speed of light, mass increases to become infinite at c. There's evidence to this. Well, why is that? Well, I think that the faster you travel, the more ether piles up on you like bugs on the windshield. Or actually, more accurately, how you get wetter when you run through the rain as opposed to walk, believe it or not. If you could sweep aside the ether, you could effectively eliminate the problem. You could then easily travel at multiples of c. You would also be isolated from the effects of inertia. If you opened a window in your ether isolation, you could ride any gravity beams in the direction you wish to travel. My 12 volt 200 amp setup is far too small. The kind of power we need is the Unilever battery bank. But the problem is you have to remember the rotor is just a conductor, a piece of wire. You can't just hook it up to a power source. You need a load bank to dissipate the power on the other end. And I don't want to just throw 1200 amps at 535 volts DC on the rotor in one blast, because that's probably exactly what you're going to have is a big blast. So now it's a major project.
So I got the battery bank, and what we need is a load bank to dissipate the power. And lo and behold, there's one right outside the battery room. And it's got a control panel here on it that where you can add the load bank resistors in increments of 50 kW, 100 kW, 200 kW, and 500 kW, totaling 1250 kW. And here are the connections for that. That's some serious juice right there. 483 phase. There's 3-phase bus bars that go through the contactors that go to the load bank fans and resistors for all the various resistive load increments. The connection from the anti-gravity unit would be made here, and we'd have to disconnect this from the generator set, and the connection would be made via this 1/0 aluminum cable I was able to borrow from a local excavating contractor. And 1/0 aluminum, I was planning to run it in parallel from the battery bank through the unit, the anti-gravity unit, to the load bank. But at the end of the day, the building owner wouldn't allow the scientific experiment to happen. There it is, 1250 kW.